So this first slide is pretty much a review of a few things that we talked about last week. We talked about chemical changes, we talked about chemical properties, but we're going to kind of put that together today. So a chemical change, again, is the ability of a substance to undergo a specific chemical change or undergo whatever we have deemed its chemical property. So for instance, we all know that iron, if it is left to the elements, will begin to rust, right? So that's why if your paint gets chipped off your car, the iron in your metal in your car will be exposed to oxygen. After a while, it will begin to rust. It's not immediate. It does take a little bit of time. But the ability to rust is its chemical property. If it actually begins to rust, it is going through a chemical change. Okay. The important part about a chemical change that I'm not sure if we talked about last week is that if you undergo a chemical change, the composition of your matter is always different. If your composition is not different, you've done a physical change. You have to completely change something in a chemical change. Okay, chemical reactions are when one or more substances are changed into new substances, but we have to call these things something else. We can't always keep referring to things as substances. Reactants are the items you start with. These are found on the left side of an equation. Your products are the items that you make during the reaction, and these are found on the right side. The important part to remember about chemical reactions are they usually have a different set of properties than what you started with. So the example I gave you last week was salt. Sodium is a reactive metal. Chlorine is a very toxic gas. You combine them together, we get sodium chloride, and we eat it on our food. Okay, completely different set of properties once you undergo a chemical reaction. Okay, so like I said a second ago, the reactants go on the left, the products go on the right, and in between we separate them with an arrow, and this is pointing towards your products. Okay, so this is probably one of the more important slides. You need to not only know this for this unit, but you need to start retaining this for the rest of the year. When we get to chemical reactions, which isn't until next semester, this has got to be second nature to you. If you don't know this by next semester, you're going to really start struggling. So first of all, to recognize a chemical change, we need to say, is energy being released or absorbed? Okay, how can we tell if energy is being absorbed? Opposite. It gets colder. If your reaction is absorbing energy, it's actually going to feel colder. If it is releasing energy, it's going to feel hotter. Okay, so if you have a temperature change, you most likely are absorbing or releasing energy of some sort. The second thing to look for is a color change. Now, why is a color change not always a good thing to look for with chemical changes? What else can a color change be associated with? Different type of change. Physical change. Usually when we change colors, it's a physical change, but sometimes it can denote a chemical change has happened. For instance, when you're cooking something and you accidentally burn it, don't you see a color change? Right, but that's a chemical change because you can't usually unburn the food that you're cooking, right? Once it's burnt, you're kind of done. Okay, the third thing you need to look for is gas production. And what I mean by gas production is you're looking for bubbling, fizzing. Sometimes it'll produce some sort of smell. Sometimes you'll see smoke. But the hard part about this is usually when we're doing chemical changes, we're adding heat. So sometimes it's not exactly bubbling, whereas it's boiling. Boiling and bubbling are two different things, so you kind of have to look at them in context. Okay, the fourth one, and for some reason this is always the hardest one for us to remember. This is the one that even my dual credit kids forget about and they don't seem to remember. So this is to recognize a chemical change. You also can see a formation of a precipitate. Precipitate is just a fancy word for saying solid. Okay, so if I start off with two liquids and I mix them together and a solid starts to fall out the bottom, a chemical change has happened. Okay, this is probably one of the better ways to recognize a chemical change. Very rarely is a precipitate going to form from a mixture in a physical change. Usually this is always going to denote a chemical change. And then lastly, we need to look to see if the reaction is reversible. Okay, if it's reversible, it's most likely a physical change. If it cannot reverse, it's probably a chemical change. Now, some chemical changes can be reversed, but they cannot be reversed easily. They require a lot more work. They pretty much require another chemical reaction to get it to reverse. Okay, and like I talked about with number 3, gas production, these are examples, these are ways, but nothing is concrete in this department. Sometimes they'll represent a chemical change, sometimes not. So you just kind of have to take them all into context. Okay, so the last thing we're going to talk about is conservation of mass. During any chemical reaction, the mass of the products is always equal to the mass of the reactants. You cannot lose mass. Okay, it had to go somewhere. All of your mass has to be accounted for. So most of you have seen wood burning at some point in time. What happens when you burn a piece of wood? Eventually you end up with a whole bunch of ashes on the ground, right? Well, the ash compared to the wood probably weighs significantly less, correct? So conservation of mass, you might think, is not being upheld. But did we really lose mass, or did we just not contain all of our mass? Where do you think the rest of the mass went? Gas form. What are the two main types that we know of? Carbon dioxide and... Remember we talked about last week, on your hands you might feel moisture, which is water. Okay, so those two things are probably coming off, and since we didn't have a giant balloon over our campfire, we were unable to collect them. It's not that they're not there, but if we had some sort of way to collect them, I bet if we were then able to weigh them, it would be the same. This theory is called the law of conservation of mass. Okay, so here we have a picture of two scales. On the picture on the left, we see two vials about halfway filled with a clear liquid, right? These are going to be our reactants. If we open them and mix the left bottle into the right bottle, we get our product. Now, what do you notice about the reactants versus the product? Okay, the reactants are clear. The product is not clear. The product is actually a yellowy orange, and if you look at the bottom, you kind of see how the bottom is not quite as clear as the top. So there's probably actually a little bit of precipitate forming there towards the bottom, so we see a chemical change happening. And if you notice, it starts out at 43.43 grams and it ends at 43.43 grams. So conservation of mass was upheld. What did they use to contain all of the products? They used a lid. So they just basically made a closed system somehow. So this is the end of chapter 2. So you have a little bit of homework. You have 6 problems. I'm actually going to do the first one with you. So the first, number 1 says, if 50 grams of sodium reacts with chlorine to form 126 grams of salt, how many grams of chlorine react? So basically, we're starting off with sodium. We are adding it to chlorine, and we are going to get sodium chloride. So I don't expect you guys to be able to write out the element equation just yet. But if you can, that'd be great practice too. But let's try to figure out if we can come up with an algebra expression. So, sodium, how many grams do we have? 50 grams. Do we know how many grams of chlorine we're starting out with? No, so I'm going to call that X. And how many grams of sodium chloride are we ending up with of salt? 126. So now what do? Subtract 50 from both sides. And we're going to have 126 minus 50 gives us 76 grams of chlorine. Okay, whatever you start off with, you have to end with. So the hardest part about this is going to be determining what are your reactants, what are your products, making sure you put them on the right side of the equal sign. So you have 5-ish minutes to do the rest of these. Hopefully you won't have any homework, but you never know. Please try to get these done before tomorrow.